All right, time for some of more examples from lesson 4. Suppose you have a piece of coaxial cable made with a solid wire at the center. The metal cylinder has a common center, hence the name coaxial, with the wire and its radius is 1 millimeter. 2 amp current flows up the center wire and a 1.5 amp current flows down the cylinder. Find the magnetic field at 4 millimeters from the center. All right, so that's my coaxial cable. The dot in the center is the center wire, and then the circle around it is my cylinder. The current is flowing up the center wire, so I have it coming out of the screen, positive 2 amps, and the current on the cylinder is going down into the screen. I have a negative 1.5 amps there. So what we do is we draw a circle around this so it has a 4 millimeter radius because I want to know the magnetic field 4 millimeters away. Well, our magnetic field is B times 2 pi r because it is B times our length. Our length is our circumference. Equals mu 0 I. Well, my radius is 4 millimeters or 0.004 meters. Mu 0 is the 4 pi times 10 to the negative 7. And then the currents are all the currents inside of my circle. Well, that's both of them. So I have to have both my currents. So we divide and we get that, which comes out to be 2.5 times 10 to the negative 5 Teslas. Now, same problem, but what if I want to find the magnetic field half a millimeter from the center? So I've got my coaxial cable. This time I'm going to draw a circle half a millimeter from the center, which will put it about there. Magnetic field times the distance, our path, the length of our path as we go around, which is our circumference, equals mu 0 I. Our radius this time is half a millimeter, which would be 0.0005. Mu 0, and this time the current is just the current inside the little circle I drew. So it's inside the yellow circles, just the 2 amps. We don't worry about the 1.5 amps. So we want just the current inside of our imaginary dotted yellow path that we made. And end up solving that, you get 8 times 10 to the negative 4 Teslas. What should the current be in the cylinder to have no magnetic field outside the cylinder? Well, if we look up here at the first equation, if I want B to be 0, either the radius has to be 0. Well, that's not going to happen because I want some distance outside the cylinder, so there'll be some radius. The mu 0 is a constant, so I need I to be 0. So I want I to be 0. So the center wire has 2 amps. That means the outside cylinder must have a negative 2 amps to get my 0 total amps of current. Another problem. If we have 2 wires, 0.2 meters apart and 2 meters long, and both carry 2 amps of current, what is the force on the wires? So there's my 2 wires. I'm having them point up towards the top of the page. And you can see the arrows representing the direction of their currents. So I find the magnetic field due to the left wire where the first wire, or where the right wire is. So you can grab that left-hand wire, thumb pointing up, your fingers will curl around, and over there by the other wire, it'll be going into the page. So my magnetic field on the right-hand wire is going into the page. I can use the magnetic field formula for a long straight wire. Fill in all the numbers. All right. We have our constant. The current said that it was 2 amps. We've got our radius, our distance. So this radius is this distance here between the wires, 0.2 meters. Because I want to find the magnetic field at the second wire due to the first wire. Multiply that together, you get 2 times 10 to the negative 6. Yay, so we know the magnetic field right there at the second wire where the X is 2 times 10 to the negative 6 Tesla. But that doesn't answer the question. We want to know the force on the wires. So we use our right-hand rule. Our fingers go the direction of the magnetic field, so they're pointing directly into the page. Our thumb goes the direction of the current, so that is going up. And your palm faces the force. Well, the palm is facing towards the left, so the force on that wire will be towards the left. The formula was ILB sine theta. Current is 2 amps. Our length of the wire, it said, was 2 meters. The magnetic field, as we just calculated, is 2 times 10 to the negative 6 Tesla. And our angle is 90 degrees. Because our magnetic field is straight into the paper, the current is straight up the paper. Those are perpendicular to each other. Multiply, you get 8 times 10 to the negative 6 newtons. And it's making the wires go towards each other. If you would like to do this easier, your book gives you a shortcut formula. The force of one wire on another parallel wire is F over L, so that's force divided by length, so force per length, the force per meter, equals mu0 times the current times the other current over 2 pi r, where r is the distance between. It's attractive, meaning the wires want to go together if the currents are in the same direction, and repulsive if the currents are in the opposite direction. So instead of doing this long problem like we just did, you are welcome to simply use this formula instead. That's all we have for now.